Okay, we are going to go ahead and take a look at one last rule even. This section is called limit rules or limit laws. And there's a first part of it that's a little more intuitive, and then that's going to give us a bigger part, something that we're going to call the squeeze theorem, or some books will call it the sandwich theorem. I like either of those names. They're both pretty good. So the first part that we need says this. It says, let's suppose that f of x is one function and g of x is another function, and we're going to assume that f of x is always less than or equal to g of x. So think about kind of what that means on a graph. Okay, that means that if g of x is up here, that f of x is always down below, or there could be spots, could be points where they're equal, but f of x is never up above g of x. Okay, so if f of x is less than or equal to g of x, then no matter what point you're talking about at A, okay, assuming that both of these limits exist, because they could not exist depending on what f of x and g of x actually are, but if the limits actually exist, then it would make sense that the limit as x goes to A of f of x could relate somehow to the limit as x goes to A of g of x, and we should be able to say something about these. Now, the tendency is to talk about one being less than the other, but remember, since f could be equal to g of x, and either all along the way or just at one specific point, the limit there has to be less than or equal for f of x there as well. So that should hopefully make sense that no matter what point A we're talking about, I mean, we could be right here where the limit for f of x and g of x are exactly the same, but it for sure can't be the case that the limit for f of x is greater than the limit for g of x. Okay, so that's just a kind of a result to have in mind, and it's going to help us get to our last result here. And we'll look at one example dealing with this. And this is going to be a good one that comes up later down the road as well. It's going to help us prove a couple of results, and it's going to give us some more interesting situations. I mentioned earlier that the rules that we have so far kind of cover about 90 to 95% of the cases that we could be talking about. The squeeze theorem covers just a small percentage of what's left over, so maybe just a few percent of the more difficult cases. Okay, so this is called the squeeze theorem. Again, some books will have it called the sandwich theorem. Either way, you kind of get the idea of what's going to end up happening here is two things are going to kind of squeeze a third thing. Or if you think about a sandwich as like two things of bread are going to kind of squeeze whatever sits in the middle of those. So here's what the squeeze theorem says. It says if, now we don't have just two functions like f and g, this time we're going to talk about three functions. So let's say we have a function f of x, and there's a function h of x that is always bigger, and we're going to have a third function g of x that's going to sit always in between them. And again, I want to kind of think about a graph here. So h of x is always the one that's bigger, and f of x is always the one that's lower, and maybe sometimes they kind of meet, but f is always down below h. Okay, and g, let's see if I can do different colors here. G has to sit somewhere in between them at every point. And maybe sometimes it's equal to h, and maybe sometimes it's equal to f, but it's always got to be between them. G can't ever be bigger than h or smaller than f. Okay. So let's suppose for a second that we have this kind of a graph and this kind of a situation here. So we have an h function, an f function, and then g sits right in between them. And suppose for a second, let's go back to black instead of blue. So suppose for a second that we have a situation where the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x. Okay, so remember, h is always bigger, f is always smaller, g is always sandwiched in between those two, or squeezed in between those two. If the limit of f of x, as x goes to a of f of x is equal to the limit as x goes to a of h of x, okay, so maybe like right here is the point A that we're talking about. Okay, we could think about what's going to happen to the limit as x goes to a of g of x, okay? So the limit as x goes to a of f of x and the limit as x goes to a of h of x, let's give that a name. I guess we'll call it L. And so saying if you have this point on your graph over here, then they both kind of are at an output of L, okay? What do you think is going to happen to the limit as x goes to a of g of x? If you said that that limit as x goes to a of g of x has to also be equal to L, then you're right. That's exactly what needs to happen there, because g can't go and limit to some other point that's higher than h or less than f if f and h kind of both kind of scope in on the same point. Then g, that has to be between f and h, also has to go to that same point. This is assuming all of those limits exist, but the limit as x goes to a of g of x has to also be equal to that value of L. Okay, so let's take a look at kind of one example where we can kind of think about this. And let me see here. Let's use this. So here's an example where instead of giving a bound, we can actually find a bound for this. So let's say we have the limit as x goes to 0. This will be the last problem we see in this video here. We have something like x squared times the sine of 1 over x, okay? Now, you may not know this, but the limit for this function is actually equal to 0. And that is not really obvious. Okay, in fact, remember our methods, method 1, method 2, method 3. Think about kind of what you could try here to be able to find the limit. Like if I didn't tell you this was equal to 0 and I just said find this, okay, think about what you would try. What would you do? Okay, and probably the first thing you would try is you would plug in 0 for x, but then you have something like 0 times the sine of 1 over 0. Okay, that's a little bit weird because 1 over 0, you could either think about that as undefined, or in some cases you would think about that as being infinitely large. How do you take the sine of something that's infinitely large? And that's weird because the sine graph goes up and down, like back and forth, back and forth. So that's a little weird to think about what's happening there as x is getting bigger and bigger, or as 1 over x, 1 over 0 here is getting bigger and bigger and bigger. This is a weird problem. And this is a weird function. Like I said, we're not going to just be dealing with functions that are kind of nice and simple like we've seen before. We're going to see some different ones, some weird ones. Okay, so this is supposed to be equal to 0. Okay, and I would say prove it. How do we know this is equal to 0? Okay, prove this. Well, this is a function that I'm going to call g of x. Okay, and if we use that squeeze theorem, then what we're going to do is we're going to try to find a function f of x that's always less than this one, and a function h of x that's always bigger than this one, and try to kind of squeeze those or sandwich those to a certain spot. So what I want to do is put x squared times the sine of 1 over x in between two other functions that are a lot easier to talk about and that I know how their limits behave. This is not quite so obvious, but think about the sine function for a second. I know there's something really complicated inside the sine function of 1 over x, but something you should remember about the sine function is that the range of the sine function is always between -1 and 1. Okay, -1 and 1. And this is because the sine function jumps back and forth from a height of 1 to a height of -1 at the bottom. It's never higher than 1. It's never less than -1. So the output here is always between -1 and 1. Okay, that means that a function f of x that you can put on the low end is actually -1 times x squared. Basically thinking about this sine function right here can never be lower than -1. I'm putting the -1 in the front so that I keep the x's on the end, but basically comparing the sine function to that -1, and then on the upper end I'm going to say 1 times x squared, and that's going to be like our h of x. Okay, so there's a lower bound and there's an upper bound on our initial function that we had at the very beginning. Okay, now that wasn't quite so obvious. We had to think about kind of the sine function and how the sine function is bounded by -1 and 1 in order to be able to set this up. But look at what happens when we look at the limit as x goes to 0 of f of x. And look at what happens when we look at the limit as x goes to 0 of h of x. Okay. What is the limit as x goes to 0 of negative x squared? Okay, let me replace an f of x here with a negative x squared. What's the limit there? And you can go back to your methods, method 1, method 2, method 3. The limit as x goes to 0 of negative x squared, you can actually just plug in 0 for x there. That's not a problem, is 0. What's the limit as x goes to 0 over here of h of x, which, remember, h of x is just 1x squared, or just x squared. And again, think about your methods. You can go ahead and plug in 0 for x. That's not a problem. You get 0 there. Okay, so you have an f of x function, an h of x function that bounds our original function g of x. And when you take the limit as x goes to 0 of both f of x and h of x, you get 0. So what is the limit as x goes to 0 of the one in the middle? X squared sine of 1 over x? Well, that's got to also be 0. Okay. By the way, here's kind of what we're saying, is that we're saying that when you take the limit here as x goes to 0 of x squared sine of 1 over x, really what this is bounded by is it's got to be less than or equal to 0, and it's got to be greater than or equal to 0. So what's that got to be in the middle? Well, it's got to be equal to 0. If it can't be less than 0, it can't be greater than 0. It's got to be equal to 0. That's the idea of the squeeze theorem, that says you can find a lower bound and an upper bound as long as your function always sits in between those two values. Okay, so this one's going to come up again in the future. Good one to have in your back pocket. That's one example, and we'll see some others in the homework. But just a good way, just a good example to hang on to, and all of these things about how to deal with limits are going to be helpful for us. Okay, hope you've enjoyed the video. Good luck in practicing.